Hello students, welcome to the video lecture 6 of the chapter Magnetism and Matter. Today's topic to be discussed are magnetization and basic terms of magnetism and magnetic susceptibility. Let us begin with magnetization and basic terms of magnetism. Here, to understand magnetism, we should learn few basic terminologies in this video lecture. So those basic terminologies start from magnetization, followed by magnetic permeability, then relative permeability, magnetic flux density, and lastly magnetic intensity. Let us begin with magnetization. Magnetization of a sample is defined as magnetic moment per unit volume. Mathematically, we can write it as m is equals to small m, that is net magnetic moment, divided by volume of the sample. SI unit of this quantity is ampere per meter. Next, magnetic permeability mu. The magnetic permeability of a material is the ability of that material to allow the passage of magnetic field lines through it. So mu naught represents the permeability of free space or vacuum. Relative magnetic permeability. So we know relative magnetic permeability can be written as mu r is equals to mu divided by mu naught. So using this equation, we can define mu r as it is the ratio of magnetic permeability of a medium, that is mu, to the magnetic permeability of the free space. For this quantity, we are having an alternate definition, that is here mu r is equal to B divided by B naught. Using this mathematical expression, we can also define relative magnetic permeability as the ratio of magnetic flux density of a medium to the magnetic flux density of free space. That is, how much magnetic flux density is there in a medium, or how much magnetic induction is there in a medium to that of magnetic induction in free space. So this is the definition of relative magnetic permeability. Moving ahead, let us now define magnetic flux density or magnetic induction. Magnetic induction at any point in a medium represents the number of field lines crossing a unit area normally through the material. So denser the magnetic field lines, more the magnetic field lines, then magnetic induction will be more. Lesser are the field lines, then magnetic induction will be less. So the one more important thing is the magnetic field lines should cross normally through an area. So the unit of magnetic flux density is Tesla, and here the other quantity that is to be defined is magnetic intensity H. The degree to which magnetic field can magnetize a material is called magnetic intensity. So magnetic intensity comes from the external field which tries to magnetize a material, and it is given by the formula H equals B divided by mu naught minus capital M. Here capital M is magnetization. Note, the SI unit of H is ampere per meter, which is same as that of magnetization. Moving to the next slide, let us now study magnetic susceptibility. Magnetic susceptibility is represented by chi. The symbol which is used here is chi. The magnetization M of a sample is directly proportional to magnetic intensity. So therefore we can write magnetization M is directly proportional to H. That is, H is due to the external field which is trying to magnetize a material. So H is an external agency which is trying to magnetize and create the magnetic dipole moment or align the magnetic dipole moments in a material, due to which the magnetization in a material will increase. So just removing this proportionality, we can try to put in the place chi. So M is equal to chi into H. So chi will be equal to M divided by H. Magnetic susceptibility is also defined as the ratio of magnetization to magnetic intensity H. And one more thing that is to be noted is M and H are having same units, thus chi becomes just a number. So chi is unitless quantity and chi is nothing but magnetic susceptibility. Now let us try to derive a relationship between mu r and chi. To do this, let us consider a solenoid of n turns per unit length carrying current I. So the magnetic field inside the solenoid is given by B naught equals to mu naught Ni, which equals mu naught into H. H is the magnetic field intensity inside the solenoid, which is equal to H equals to N into I. So let us take this as equation 1 and let us proceed ahead. If the interior of the solenoid is filled with a material whose magnetization is non-zero, that means it already is magnetized, which already has some magnetic field due to it, which can create an extra magnetic field. So if it is that case, then the net magnetic field inside the solenoid will enhance, that means it increases. So we can write the net magnetic field inside the solenoid to be B equals to B naught. B naught is because of the current and plus Bm. Bm is because of the material which is kept inside the solenoid. So let us take this as equation 2 and let us proceed here. Bm is the contribution because of the material core as said previously, and here Bm is proportional to magnetization. So how much it gets magnetized, so much only magnetic induction will be there in that material. So we can write Bm is equal to mu naught M. Taking this as equation number 3 and substituting the values of 3 and 1 in equation 2, we get the equation to be B is equal to mu naught H plus mu naught M, and we see that mu naught is common in both the terms. So we take mu naught common and retain H plus M inside the bracket. Taking this as equation 4, let us proceed next. We know that M is equal to chi H. So substituting this in our equation 4, we get B is equal to mu naught into H plus chi H. Taking H common, we get mu naught 1 plus chi into H. We can replace 1 plus chi with mu r, because we see that mu r is the quantity that has to be present over there. So B is equal to mu naught mu r into H. So we see that B is equal to mu into H. Here mu is the permeability of the material that is placed inside the solenoid. So the net magnetic field is written in terms of the permeability of the material which is placed inside the solenoid. So we can write the relationship between mu and chi as this one, that is mu r is equal to 1 plus chi. So this equation relates mu r and chi. Thank you students, and see you in the next video lecture.